Dear students, in this video we are going to study about the electrostatic potential energy and electrostatic potential. Electric potential due to a point charge, electrostatic potential at a point due to an electric dipole, equipotential surface, then the relation between electric field and potential, electrostatic potential energy for a collection of point charges, electrostatic potential energy of a dipole in uniform electric field. Now let us study about electrostatic potential and potential energy. Introduction. In mechanics, we know that the potential energy is defined for conservative forces. Since gravitational force is a conservative force, this gravitational potential energy is defined in standard 11. Since Coulomb force is an inverse square law force, it's also a conservative force like gravitational force. Therefore, we can define potential energy for a charge configurations. Now, we will see about the electrostatic potential energy and electrostatic potential. Consider a positive charge Q kept fixed at the origin, which produces an electric field E around it. A positive test charge Q dash is brought from point R to point P against the repulsive force between Q and Q dash, as shown in the diagram 1.20. So work must be done to overcome the repulsion between the charges, and this work done is stored as potential energy of the system. Here we see that the microwave oven works on the principle of torque acting on an electric dipole. The food we consume has water molecules, which are permanent electric dipoles. The oven produces microwaves that are oscillating electromagnetic fields and produce torque on the water molecules. Due to this torque on each water molecule, the molecules rotate very fast and produce thermal energy. Thus, the heat generated is used to heat the food kept inside the oven. And now you see that there are two charges, plus Q and the charge Q dash kept at a distance, and it is moved to the point P. And this test charge Q dash is brought from R to P with constant velocity, which means that the external force is to bring the test charge Q dash from R to P must be equal and opposite to the Coulomb force. So the force external that's equal to minus F Coulomb. The work done is given by W equal to integral R to P F external dot dr. Since Coulomb force is conservative, work done is independent of the path and it depends only on the initial and final positions of the test charge. If potential energy associated with Q dash at P is given by UP and that at R is UR, then the difference in potential energy is defined as the work done to bring a test charge Q dash from point R to P, and is given as UP minus UR equal to W, and that's given by delta U. This delta U is the difference in energy. And delta U is given by integral R to P F external dot dr, and here as external force is given by the negative of Coulomb force given by minus Q dash times E. So the difference in energy is given by integral R to P plus minus Q dash E dot R dr, that's equal to Q dash integral of R to P minus E dot dr. So the potential energy difference per unit charge is given by this equation 1.29, and the equation is independent of Q dash. So the quantity delta U by Q dash is given by minus integral R to P E dot dr, and that is called as electric potential difference between P and R, and is denoted as Vp minus Vr equal to delta V. Otherwise, we can also say that the electric potential difference is defined as the work done by an external force to bring unit positive charge from point R to point P. So we have this equation 1.30, which is given by the difference between the potential at the point P and R, that is Vp minus Vr equal to delta V equal to integral R to P minus E dot dr. The electric potential energy difference can be written as delta U equal to Q dash delta V. Basically, potential difference between 2 points is a meaningful quantity. The value of potential itself at one point is not meaningful. Therefore, the point R is taken to infinity and the potential at infinity is considered as 0. So, V infinity equals 0. So, we can say that the electric potential at a point P is equal to the work done by an external force to bring a unit positive charge with constant velocity from infinity to a point P in the region of the external electric field E. This can be written mathematically as Vp equal to minus integral infinity to P E dot dr. Now you will see about the important points to be considered. The first case is about the electric potential at the point P depends only on the electric field, which is due to the source charge Q and not on the test charge Q dash. The positive charge is brought from infinity to a point P with constant velocity because external agency should not impart any kinetic energy to the test charge. And the second point is from the equation 1.29, the unit of electric potential is joule per coulomb, but practical unit is volt, named after the scientist Alessandro Volta, who invented the electrical battery. The potential difference between the 2 points is expressed in terms of volt. And the next topic is about the electric potential due to a point charge. So if you consider a positive charge Q kept fixed at the origin, then let P be a point at a distance r from the charge Q, as shown in the diagram 1.21. The electric potential at the point P is given by V equal to integral infinity to r minus E dot dr, and thus given by negative of integral infinity to r E dot dr. So the electric field due to a positive point charge at Q is given by E equal to 1 by 4 pi epsilon Q by r square r cap, and V is given by minus 1 by 4 pi epsilon integral infinity to r Q by r square r cap dot dr. The infinitesimal displacement vector dr is given by dr dot r, and using r dot r equal to 1, we have this equation, that is V equal to minus 1 by 4 pi epsilon naught integral infinity to r Q by r square r dot dr dot r cap, and thus given by minus 1 by 4 pi epsilon naught integral infinity to r Q by r square dr. So after the integration, we have this equation V equal to minus 1 by 4 pi epsilon naught Q into minus 1 by r infinity to r, the limits. And that's given by 1 by 4 pi epsilon naught Q by r. Hence, electric potential due to a point charge Q at the distance r is given by V equal to 1 by 4 pi epsilon naught Q by r. Now let us see the important points. If the source charge Q is positive, then the potential V is greater than 0. And if Q is negative, V is negative and is equal to V equal to minus 1 by 4 pi epsilon naught Q by r. And the second point is from the expression 1.33, we have that the potential due to positive charge decreases as the distance increases, but for a negative charge, the potential increases as the distance is increased. At infinity, that means r is equal to infinity, electrostatic potential is 0. That means V equal to 0. In the case of gravitational force, mass moves from a point of higher gravitational potential to a point of lower gravitational potential, as you see in this diagram. Similarly, a positive charge moves from a point of higher electrostatic potential to a point of lower electrostatic potential. However, a negative charge moves from lower electrostatic potential to higher electrostatic potential, and this comparison is shown in this 1.23. Yeah. Then the third case is the electric potential at a point P due to a collection of charges Q1, Q2, Q3, etc. is equal to the sum of the electric potentials due to individual charges, as given in 1.34. Where R1, R2, R3, etc. up to Rn are the distances of Q1, Q2, Q3 and up to Qn respectively from the point P. So here you see there are a number of charges Q1, Q2, Q3, Qn, which are at the distances R1, R2, R3 and Rn. So in this example, the electric potential has to be calculated at different points. Then you have this topic, electrostatic potential at a point due to an electric dipole. For this, let us consider two equal and opposite charges separated by a small distance 2a, as shown in this diagram. There are two charges plus q and minus q separated by a distance 2a. And the point P is located at a distance r from the midpoint of the dipole. Let theta be the angle between the line OP and dipole axis AB, and R1 be the distance of the point P from plus Q, that is R1, and R2 is the distance of point P from minus Q. So the potential at the point P due to a charge plus Q is given by 1 by 4 pi epsilon Q by R1, and the potential at the point P due to a charge minus Q is given by minus 1 by 4 pi epsilon Q by R2. So the total potential at the point P is given by V equal to 1 by 4 pi epsilon Q into 1 by R1 minus 1 by R2. Suppose if the point P is far away from the dipole such that R is very much greater than A, then the equation 1.35 can be expressed in terms of R like this. So by the cosine law for triangle BOP, we have R1 square equal to R square plus A square minus 2RA cos theta, and R1 square is given by R square into 1 plus A square by R square minus 2A by R cos theta. Since the point P is very far from the dipole, R is very much greater than A. As a result, the term A square by R square is very small and can be neglected. So we have Rn square equal to R square into 1 minus 2A cos theta by R, or R1 equal to R into 1 minus 2A by R cos theta power half. And that can be written as 1 by R1 equal to 1 by R into 1 minus 2A by R cos theta power half minus half. Since A by R is very much less than 1, we can use binomial theorem and retain the terms up to the first order. So we get the equation 1.36 like this: 1 by R1 equal to 1 by R into 1 plus A by R cos theta. Similarly, you can apply the cosine law for the triangle AOP, and we have this equation for R2 square, that's given by R2, R square plus A square plus 2RA cos theta. And here also we neglect the term A square by R square because R is very much greater than A. So we have R2 square equal to R square into 1 plus 2A cos theta by R. And therefore we have 1 by R2 equal to 1 by R into 1 minus A cos theta by R. So substituting the equations 1.37, 1.36 in the equation 1.35, we have this equation V equal to 1 by 4 pi epsilon R2 AQ by R square cos theta. But the electric dipole moment P is given by 2QA, and therefore this equation can be written as V equal to 1 by 4 pi epsilon P cos theta by R square. So we can write P cos theta equal to P dot R, where R unit vector is from the point O to a point P. Since the electric potential at a point P due to an electric dipole is given by this equation 1.38. So this equation is valid for the distances very large compared to the size of the dipole. But for a point dipole, the equation 1.38 is valid for any distance. Now we will consider the special cases. In the first case, if the point P lies on the axial line for which theta equals 0, that is the point is on the side of plus Q, then the electric potential will be given by V equal to 1 by 4 pi epsilon P by R square. And in the second case, if the point P lies on the axial line for which theta equal to 180 degrees, that means the point P lies on the side of minus Q, then you have the equation as V equal to minus 1 by 4 pi epsilon P by R square. And in the third case, if the point P lies on the equatorial line of the dipole, then theta equal to 90 degrees, therefore V is equal to 0. Now you see that the potential due to an electric dipole falls as 1 by R square, and the potential due to a single point charge falls as 1 by R. Thus the potential due to a dipole falls faster than that due to a monopole, that is a point charge. As the distance increases from the electric dipole, the effects of positive and negative charges nullify each other. Next we study about the equipotential surface. For this, let us consider a point charge Q located at some point in space, and an imaginary sphere of radius R is chosen by keeping the charge Q at its center. The electric potential at all points on the surface of the given sphere is the same. Such a surface is called an equipotential surface. So what is an equipotential surface? An equipotential surface is a surface on which all the points are at the same electric potential. So we can write like this. For a point charge, the equipotential surfaces are concentric spherical surfaces as shown in figure 1.26b. Yeah. And each spherical surface is an equipotential surface, but the Value of potential is different for different spherical surfaces. So for a uniform electric field, the equipotential surfaces form a set of planes normal to the electric field E, as shown in the figure 1.27, like this. So these are the planes having equipotential surfaces in a uniform electric field. And what are the properties of these equipotential surfaces? In the first case, the work done to move a charge q between any 2 points A and B is given by W equal to Q into VB minus VA. If the points A and B lie on the same equipotential surface, work done is 0 because VA equal to VB. And the second one is the electric field is normal to an equipotential surface. If it is not normal, then there is a component of the field parallel to the surface. Then work must be done to move a charge between 2 points on the same surface. This is a contradiction. Therefore, the electric field must always be normal to equipotential surface. Next, we will study about the relation between electric field and potential. For this, let us consider a positive charge Q kept fixed at the origin. To remove a unit positive charge by a small distance, that is, we are considering that the unit positive charge is moved through a small distance dx towards Q in the electric field E. Then the work done is given by dW equal to minus E dot dx. The minus sign implies that work is done against the electric field. This work done is equal to electric potential difference. So we have the equation dW equal to dV, or dV equal to minus E dx. So E is given by minus dV by dx. The electric field is a negative gradient of the electric potential. So you can write like this in the vector form as given in 1.44, like this. Next, we are going to study about the electrostatic potential energy for a collection of point charges. The electric potential at a point at a distance r from the point charge Q1 is given by V equal to 1 by 4 pi epsilon Q1 by R. This potential V is the work done to bring a unit positive charge from infinity to the point. Now, if the charge Q2 is brought from infinity to that point at a distance r from Q1, the work done is the product of Q2 and the electric potential at that point. So we have W equal to Q2 times V. This work done is stored as the electrostatic potential energy U of a system of charges Q1 and Q2 separated by a distance r. So we have this equation U plus Q2 times V equal to 1 by 4 pi epsilon Q1 Q2 by R. The electrostatic potential energy depends only on the distance between the 2 point charges. In fact, the expression 1.45 is derived by assuming that Q1 is fixed and Q2 is brought from infinity. The equation 1.45 holds true when Q2 is fixed and Q1 is brought from infinity, or both Q1 and Q2 are simultaneously brought from infinity to a distance r between them. Three charges are arranged in the following configuration as shown in figure 1.28, like this. To calculate the total electrostatic potential energy, we use the following procedure. We bring all the charges one by one and arrange them according to the configuration as shown in this diagram 1.28. So here you have Q1 at A, Q2 at B, Q3 at C. They are separated by these distances R12, R23, and here R13. So in the first case, bringing a charge Q1 from infinity to the point A requires no work because there are no other charges already present in the vicinity of charge Q1. But in the second case, to bring the second charge Q2 to the point B, work must be done against the electric field created by the charge Q1. So the work done on the charge Q2 is given by W equal to Q2 times V1B, where V1B is the electrostatic potential due to the charge Q1 at the point B. So you have this equation 1.46. That is U1 is given by 1 by 4 pi epsilon Q1 Q2 by R12. You see that this expression is the same when Q2 is brought first and then Q1 later. The third one, similarly, to bring the charge Q3 to the point C, work has to be done against the total electric field due to both charges Q1 and Q2. So the work done to bring the charge Q3 is given by Q3 times V1C plus V2C. Here V1C is electrostatic potential due to charge Q1 at point C, and V2C is the electrostatic potential due to charge Q2 at the same point C. The electrostatic potential energy is given by this equation 1.47. And the fourth one is, if you add the equations 1.46 and 1.47, the total electrostatic potential energy for the system of three charges, Q1, Q2, and Q3, that's given by U equal to U1 plus U2. So we get this equation 1.48, and we note that this stored potential energy U is equal to the total external work done to assemble the three charges at the given locations. So this expression 1.48 is the same if the charges are brought to their positions in any other order. Since the Coulomb force is a conservative force, the electrostatic potential energy is independent of the manner in which the configuration of the charges is arrived at. And the next topic we are going to study about is electrostatic potential energy of a dipole which is kept in a uniform electric field. For this, let us consider a dipole placed in the uniform electric field E as shown in the diagram. And this dipole experiences a torque when kept in a uniform electric field E. This torque rotates the dipole to align it with the direction of the electric field. It rotates the dipole with constant angular velocity from its initial angle theta dash to another angle theta against the torque exerted by the electric field, and equal and opposite external torque must be applied on the dipole. Here you see that a dipole is kept in uniform electric field. The work done by the external torque to rotate the dipole from angle theta dash to theta at constant angular velocity is given by this equation 1.49, and since this external torque is equal and opposite to the torque tau E equal to P cross E, we will have this equation, that is external torque equal to tau E equal to P cross E. So substituting this equation in 1.49, we have this W equal to P times cos theta dash minus cos theta. This work done is equal to the potential energy difference between the angular positions theta and theta dash. So U theta minus U theta dash equal to delta U equal to minus P cos theta plus P cos theta dash. If the initial angle is theta dash equal to 90 degrees, it is taken as a reference point, then U theta dash is given by P cos 90 degrees plus equal to 0. The potential energy stored in the system of dipole kept in the uniform electric field is given by this equation 1.451, that's U equal to minus P cos theta, that's given by minus P dot E. So in addition to P and E, the potential energy also depends on the orientation theta of the electric dipole with respect to the external electric field. The potential energy is maximum when the dipole is aligned anti-parallel, that means theta equal to pi, to the external electric field, and that will be minimum when the dipole is aligned parallel, that means theta equal to 0 to the external electric field.
Why are there not more people talking about electrostatic potential? It turns invisible forces into a map you can read. Think of charge as a mountain. Equipotential surfaces are contour lines. Every point on a surface has the same potential. A positive test charge rolls downhill from high to low potential. It never crosses an equipotential without effort. Closer lines mean stronger fields. Learn this and you'll visualize fields. Learn this and you'll visualize forces. Learn this and you'll visualize why charges move.